So here's the master system diagram for our final SmithVent design. It's actually not too different from the version that we proposed at the end of round one. I'm going to talk you through it, and I'll focus on the airflow pathway through the system. So we started with compressed air and oxygen supply at the hospital wall, which is pressurized to about 50 pounds per square inch. The air and the oxygen lines both have inline air filters, and there's a set of one-way check valves to prevent reverse flow. The back wall of the ventilator has disc fittings that ensure the two lines can only attach to their intended ports and not accidentally be reversed. After entering the ventilator, the air and the oxygen then go through the first set of solenoid valves, which we call SV1 and SV2. These act as on-off switches to control how much of either gas can pass through. The air and the oxygen are then combined in the mixing reservoir. For ease of speaking, I'm going to refer to the gas mixture as air or airflow for the rest of this section, but keep in mind that it could contain up to 100% oxygen, depending on the system settings. We continually measure the pressure in the reservoir using a pressure sensor and control the opening of the first two solenoid valves to keep the reservoir pressure between 10 and 25 psi. So then the airflow exits that far end of the reservoir. It goes into what we call the inspiratory line. The first component on the inspiratory line is the proportional solenoid valve, or SV3, which allows fine control of the flow passing through, something like a very precise dimmer switch. Inspiratory line also has a pressure sensor and a flow sensor, and we use that data to control the proportional solenoid valve, as Neilani will discuss later. And the last component on the inspiratory line is a pressure relief valve, which is an additional safety measure to limit the airflow pressure going to the patient. The airflow then exits the ventilator and travels through the patient breathing circuit. On the way to the patient, it passes through a HEPA HME device that provides heat and moisture exchange going to the patient, and then filters the breath coming from the patient. This filter is especially important in COVID-19 cases to protect the healthcare workers from airborne coronavirus particles and prevent cross-contamination between patients. Having gone through the filter, the patient's expired breath then travels back to the ventilator. And it enters the expiratory line, where it goes through a one-way valve to keep the patient from accidentally inhaling their recently expired breath. The expiratory line also has a pressure sensor and a flow sensor to collect data for system controls. The solenoid valve on the expiratory line, SV4, is also an on-off valve, like the first two, except that its resting state is normally open rather than normally closed. This means that in case of mechanical failure, the patient will always be able to exhale. It's worth noting here that SV3 and SV4 alternate so that inspiration and expiration can't happen at the same time. And the last stop on this airflow journey is the PEEP valve, which provides a small amount of back pressure to help prevent the alveoli from collapsing. After going through the PEEP valve, the expired breath then joins the ambient air. And now I'll turn it over to Dan to explain the electrical components that control the whole system.
So next, I'll introduce the electrical system. The brain of the system is a microcontroller board, Arduino Mega. Then there are 5 sensors in the system, 3 pressure sensors and 2 flow sensors. We also have 4 solenoid valves and their controllers, and a user interface, including a touchscreen display with a level shifter, 1 buzzer, and 2 LEDs. And last but not least, the power management components. All the electrical components are off the shelf and were selected based on system requirements. Then I'm going to talk about how signal flows through all these components. The microcontroller takes input from all the sensors and sends outputs to a 4-channel relay board for SV1, 2, and 4, and a pulse width modulation controller, which is necessary for the proportional valve SV3. The microcontroller also controls the user interface components, as well as processing clinician inputs through the touchscreen. In terms of power management, the whole system can be powered by a wall adapter, which converts 120-volt AC to 12-volt DC. The 12-volt supply powers a 5-volt voltage regulator, the Arduino Mega, and the valve controllers. The sensors are powered by 5 volts from the Arduino. as well as the buzzer and the LEDs. While the touchscreen is powered by a 5-volt regulator due to its high current that Arduino can supply. The level shifter, which converts logic signals, is powered by both 5 volts and 3.3 volts from the Arduino. The whole electrical system can be professionally represented by schematics and a wiring diagram, shown here on the slide.